Thanks, Matt, for the introduction, and thanks that you decided to come to my Experience report. My name is Florian. I'm from Siemens. I call myself a test architect. I do mostly research and consulting in topics of test architecture, test management, and overall system quality. From the topic of my talk, and because in particular of my profession, you might expect me now to talk exclusively about testing, but this is not quite the case, don't worry. Also, tests will play an important role in my presentation, and they also be the overall goal of all the things I'm going to talk about. And the reason is that tests are not only very important for any kind of system, but they are especially hard to perform in a reliable manner for cyber-physical systems, and the reason is, of course, the relationship to physics, to mechatronics, and the notion of their interaction with a somehow unpredictable environment. And after this first short definition, and just out of curiosity, who in here is working with such a cyber-physical system? I know one at least, because we talked at the breakfast. So 3 at least. Okay, I think you hopefully will agree that the issues that I told are even worse if we talk about safety critical functions that should execute right in time even when single components of the cyber physical system fails. And that is exactly what I will talk about in this report. Safety critical system that should execute right in time. It has real-time properties and is distributed in nature in order to be fail-safe. I also explain how we can obtain reliable statements, as the topic is saying, and how we can also test this system. This is not only important for system development on the one hand, but also for maintenance and operation in the lab and also in the field, and of course for certification purpose. Before I dive into deep of this topic, what should you ideally take away out of this presentation? I want to leave you with 4 key messages. So my basic hypothesis is that we can obtain these reliable statements from this cyber physical system, that is testable itself. And in our case, this testability comes from so-called test probes. It's right here. Now I lost my microphone, sorry for that. Sorry. These test probes are special hardware-software components that are built into the system by design, and they stay there throughout the whole software life cycle. These test probes are built into each node of this distributed system, and they also remain there during operations. This is done in order to non-intrusively monitor, because they stay in there, they have their own time slot, so we can non-intrusively monitor, manipulate and test system data as well as system signals and data flows. By doing this, we have no effect on a system under test, because these test probes are a homogeneous integral part of each of the system nodes. The test probes can also be programmed. That is used to enable automated testing. And central for these automated tests are these invariants. So invariants are statements on states and signal of the nodes, and this invariance should stay constant from cycle to cycle in this time-triggered system, or only change within slight limits. I'd also come back to this slide at the very end of my presentation. So how have I structured this presentation? My goal is to show you for which system properties we want to have these reliable statements, and how can we test this reliably. And therefore, I first show you systems and properties that a user has to rely on. After that, I pick one of the properties and will explain it in detail. In the third part, we will use this formally explained property and derive testable statements out of it. And these testable statements will be the base for test cases that we will derive together in several stages. These test cases are formulated using a DSL that we developed specifically for this project. And I'll show you also this DSL. At the end, to get these reliable statements for the safety critical system that should execute right in time within milliseconds, it's of course not only enough to formulate the test cases, but also the system under test has to cooperate. And I'll show you also which measure we used to get this reliability. So, reliable statements, what am I talking about? As quick example, as a road user, and that is anyone participating on the road, because our cyber-physical system will be an eCar. So as a road user, I must rely on statements with even thinking about it. And it's the driver, but it's also everyone that's participating on a road. And in our case, the statement is that the eCar steers safely even when any of the redundant components of this eCar fails, temporarily or also permanently. You can see some of these redundant components on the right. And by any components, I'm speaking of the control unit, a sensor, or even the redundant power circuit. And this idea of critical system properties is not only true for eCars, of course, but it can be transported to any domain. So let's have a small excursion to the robotic domain. And you might remember this example of the mobile assembly robot if you attended my colleague Markus Lachenmeyer's talk on connectors yesterday. And just as example, we want to be sure that the manipulator here, that in operation there is no accident in human-machine or machine-machine interaction, and therefore there are of course several critical system properties that should be fulfilled, that should hold all during the operation time. But back to the road. What am I talking about? So this critical system property I'll show you in a scenario. Here we have the scenario of the safe steering function in 3 phases. In the first phase, you can see unhappy driver. He's reading his newspaper. He can do this because he's, of course, driving autonomously. You see that there are 2 components in the car. There's a dark green one, that's the component that's at the moment executing the steering function as authority. And there's a backup component in there, that's the bright green one. So in phase 1, we are safe. We have 2 components at all. In the next phase, all of a sudden, something dangerous happens, and the component that is at the moment the primary, the former dark green one, shuts down. So for a short period in time, there is no component at all that's now executing the steering function as authority. The driver is unaware, but of course, that's a dangerous situation. Fortunately, in the last phase, the former backup component gets promoted to a new primary one. So at the end, everything is fine. We have a happy end. The driver is still unaware, but now should, of course, be informed that there's a problem and that he has to go to service. So having seen this scenario, let's analyze it phase by phase. Back again in the first phase, we see the happy driver. There are again 2 components in there, the dark green one, that's the authority for the steering function, and the bright green one as backup. And if we look at the center of the slides, we can see that the authority component is called primary component, and here's the backup component. And each of these components are actually consisting of 2 nodes each. So for the primary component, we have node 3 and node 4. And so it's called a dual node. So we have 2 dual nodes in here, and the primary component, the nodes, node 3 and node 4, they are monitoring each other. So they can see each other's state and can see what happens. The same is true, of course, for the backup component. We can see that there are 2 redundant sensors on the left, the steering sensors, and we have 2 redundant steering boxes on the right that are controlling the wheels. The steering sensors are sending the data to the primary component, but also to the backup component, and they're doing this clockwise and counterclockwise to also get redundancy here. On the other side, we can see that the steering boxes are just getting their data out of the primary component. So that's the master component for the steering function. The other one is just in hot standby. So we have 2 components, 2 dual nodes, and we are in safe mode. So now again, all of a sudden, for whatever reason, something dangerous happens. Node 3 and node 4 that are monitoring each other, they detect an inconsistency and they decide to shut down a system. So for this short period of time, there is no primary component, there is no one as authority executing the steering function. Nevertheless, these steering sensors are sending their data to both components, but now we see that the steering boxes aren't getting any comments at all. I think we can agree that this is a dangerous situation and that the eCar integration platform, that's the thing we're seeing here, has to detect it and has to repair it silently. So the driver wants to be unaware, reliably of course, and especially quickly. Fortunately, that's exactly what happened. So in the third phase, we see that the former backup component was promoted to the primary one, and these components are of course also exchanging data. So these sensors are still sending data to both, but now the actors, the steering boxes, are getting their commands from the new primary component. Everything is fine. The driver is still happy, still reading, but now has of course to be informed that he has to go to service, because in vulnerable mode there is no longer backup, and of course we need a new one and it has to be repaired. Having seen this, how does the system under test look like? No, first we see again a critical system property. So the property says again that the eCar steers safely even when the redundant component fails, and we see again the three phases. And to test this before we see the system under test, we have of course to derive testable statements, testable requirements. And in our case it is that critical apps run on at maximum one primary component, so we always had just one. In safe mode there are at least two components running the critical app, so we have a primary component and a backup component. In dangerous mode, the critical apps run without a primary component for a specified numbers of cycles. We called Y, and this Y is dependent on the task, so in our case the steering function, but also the state, the environment, so what's the weather, how fast are we driving, and things like that. And in vulnerable mode, critical apps run on exactly one component here, and this has to be the primary one. Now we see the system under test. That's the central integration platform, and essentially for our test cases for our system are again the two nodes we see here. On the top again the primary component consisting of node 3 and node 4, and the backup component consisting of node 5 and node 6. We also see again the two redundant sensors and the two redundant steering boxes. And that's now the first time that you can actually see the test probes that I promised you at the beginning. So we have dedicated test probes that are integral part of each of the system nodes, and we'll use then some slides later. The sensors and the steering boxes are part of the platform periphery, and they are connected to the inner nodes by a so-called outer ring. That's the gray one. They can communicate. And we saw also that the inner nodes can communicate, and they are using this inner ring. That's the black one here. On the right, you can see the actual hardware. So each of this is one dual node consisting of two twin nodes each. And you can see the dedicated ports. So we have ports for the inner ring and the outer ring each. And you can also see that we have a redundant power circuit. So the red one for the upper nodes and the blue one for the nodes on the lower side, because a cut through the power circuit would be a single point of failure. And so also we need redundancy here. So what's the basic test idea now? The basic test idea is to restrict the test scope to just two of the nodes of each of the different dual nodes. So we're taking one node of the upper dual node of the primary component and one node of the lower dual node. And the reason is that we can exploit the fact that for corrupting the state of, for example, the primary component, it's enough to corrupt the state of just one of its constituting node, because they, as I said before, are monitoring each other and therefore will find the error and shut down. You can see the basic test idea on the right. For the steering function, we want to start in safe mode. That is, we need a primary node for the steering function, that's node 3. We need a backup component for the steering function, that's node 5. And now to get into dangerous mode, we need to shut down one of the nodes, and we are doing this by injecting an error in the state of node 3. Now the system, the two nodes of the primary component will detect this inconsistency and therefore will shut down. And hopefully, after a period of time, the former backup component, node 5, will be promoted to the new primary one, and we end up in the vulnerable mode. And if that's the case, the test case will succeed. So after all this explanation, we are finally ready to have a look at the first real test case. Wow, and I have to admit that's a heavy one, just right before lunch. But don't worry, we will have a short walkthrough together. So we see that we want to test a critical app. That is our steering function, and we want to be sure that it continues even when the primary component fails. Therefore, again, we need two nodes, node 3 and node 5. And just let me jump back. These are node 3 and node 5 of the two different dual nodes. And we want to inject an error in the state of node 3 starting at cycle 10 for 3 cycles. And that's exactly what we do on the right. We need the primary component that will be the node 3. The backup component will be the node 5. And we are using the invariants I promised you at the beginnings. So this invariant will be checked in each cycle, and it has to be true in each cycle. And our invariant is defined as either node 3 is primary or node 5 is primary. That was the first requirement we saw at a slide with the critical system properties. The test will start because our trigger is fulfilled. And so at cycle 10, we start to inject an error in the state of node 3 starting at cycle 10 for 3 cycles. And we continuously checking the invariant. And also this test seems pretty simple. Unfortunately, you can also see it on top. It's not working at all and also not reliable therefore, because we are ignoring the fact that the system needs time to detect the error on the one hand, but also it needs time to switch the node, so to switch node 5 from backup component to primary component. So we need to open up a window for the system to run without primary, and that we'll see in the next test case. Here we see that we extended, that we weakened the invariant, so now the invariant is true if either node 3 is primary or node 5 is primary or node 5 is still backup, because the component hasn't switched yet. Now, thinking back to requirement 3, that the system runs without a primary component for a specified maximum number of cycles, I think we can clearly see the new problem now. Node 5 could be stuck forever now as backup component. We wouldn't detect that. The test nevertheless will succeed, so it's probably less reliable than it was before. And we need further enhancement, and that we'll see in the third and final test. Now we added an additional assertion, so we're using the same invariant as before, but we added an assertion, and we are checking at a specified point in time. In our case, it's the time you start injecting the error, the time you need to detect the error, and the time to switch. And at this point in time, we are checking that the former backup component, node 5, is promoted to the new primary. At this point in time, we need to have the new primary to fulfill requirement 3. So for the 4 requirements we specified out of the critical system properties, this is a reliable statement, a reliable test. But of course, you might ask now, what will happen after this point in time? Are we sure that the node 5 not jumps back to just being backup? And if you thought about that, of course, you are right. But that was not specified in our requirements, and we also could handle that case. I just won't show it in this presentation, so you have to trust me in this case. The DSL that we are used also has tools to handle looking back in time and doing this kind of detections. As I said at the beginning, it's of course not enough to just write the test cases using the DSL that we developed. Also, the system as a test has to cooperate, of course. And if we think back to the picture on the left, that's the system under test that we saw at the beginning with the different nodes, with the primary backup components and the sensors and steering boxes. On the right, that's exactly the same picture, but from a test system point of view. And here you can see one important measure that we are using for non-intrusiveness and for testability. We are using a completely separated network in the eCar. So it's really a physically separated network as example of exclusive hardware-software resources. And you can see on the bottom, again, the actual hardware with the inner and the outer ring each. And there are 2 ports left, and even these 2 ports are dedicated ports just for the test network. You can see that the test network is organized as star. So we have the test controller in the center, and it's connected to each of the distributed test probes to guarantee a fast peer-to-peer connection here. So we can stay in the time slots that we have in the time-triggered cyclic system. That's, of course, not the only measure that we are using. There are multiple ones. And I just want to pick out 4 of them on the next slide. We are in a time-triggered system, as I said before, and we can use this cyclic time-triggered system because here we are in control and not the environment as it would be in an event-triggered system. And therefore, we can guarantee a deterministic behavior and therefore also deterministic tests for the system. We have a data store in each node that is not to be confused with a real database. It's a memory area where modules and drivers of the node can store data and read data in their own part each, and it's also used for communication. So all the communications inside the modules, inside the services runs using this memory area. One such module is the test probe that is built in by design. So it has it on its own time slot. It's non-intrusively usable. And this test probe is the only one that can read and write the complete memory area. That's what we did in test cases. We wrote an arrow, we injected an arrow in the state of the database. And we saw at the last slide that we had a dedicated network as example of exclusive hardware-software resources that we, of course, also need to non-intrusively test to have no implication on a runtime at a system under test. Thinking back to the picture of the hardware that you saw or to the dual node, we now have a look at a single node. So here again is the complete hardware with the component with node 3 and node 4. And that's a picture of just one node. So in that example, it's the node 3. You can see the database residing in the center. And we have a scheduler that's cyclically time-triggered, and it's scheduling platform services and platform applications. We have an I/O manager that is such a platform service that's needed to get data from the network and store it into the database. And we see that also the test probe is such a service that is scheduled, time-triggered cyclically, and that can access the database. And as I said before, the test probe is the only one that can read and write in every of these areas. The test probe again has this dedicated connection to the central test controller, and the test probe is controlled with test parameters and test procedures as we saw in our test cases. The test parameters, procedures, but also verdicts can be transported from and to the central test controller and can be gathered there. This being the last picture of my presentation, I want to go back to its very beginning, although there are, of course, a lot of topics we haven't talked about today, like how to set up and tear down the test or the test system, and how to do this in production. And of course, there are a lot of more topics that would be interesting. But let me recap today's session. So we saw that we want to get reliable statements from critical system properties. In our case, that was that the eCar still steers safely even when any redundant component fails. We tested this using probes that are residing in each node by design, and we used these probes in a test case. So we wrote node 3.state, and we injected an arrow, and we also used it in the invariants. And the invariants were used to test cyclically. They had to creep through each cycle on states, signals, and data flows. So we checked that either node 3 or node 5 was the primary component. We can do this non-intrusively, as I said before, because we are using exclusive hardware or software resources. We are using a test probe that can access the data store, and I showed you the list with a lot more of the measures. Having said this, I'm at the end of my presentation. If there are any questions, I happily answer them now, or you can also contact me at any time. Thanks for the attention. Yeah.
So the test probe is a module running in like the host node ECU, right? How big is the footprint? And you said it executes at the end of the normal cycle. How much load does that put on the CPU that wouldn't otherwise be seen like when you're not testing?
Yeah, the question was, what's the footprint of the test probe? As I saw in many of the other topics, that depends, of course, because you can tell the schedule. So you have to think beforehand how much time you want to give the test probe in this cyclic system. But it will be the same time. So it will be the same time in every cycle, of course. And it's not lost because you can use it, for example, for monitoring if you are in operation. So you use it for testing if you're in a lab, and you can use it for monitoring functions if you are in operations, for example. But the footprint really depends on whatever you decide for the schedule.
So when you have it deployed in the actual vehicle operationally, is that test port feature still operational, or is it disabled?
Yeah. So the question is if the test system is still operational while we are on the road. It is disabled because you, on the one hand, unplug the test system. So the central test controller is on the outside. So we've seen the dedicated ports. You can unplug it, and we can use this time slot for monitoring. And if you are at service, for example, you can plug it in and read out the data. But we don't do intrusive injections on the road, and also no one else could do that.
So we have stuff like that for a lot of our systems
that
are not safety critical, but safety critical requirements usually say if you have code that's running in there that can actually create a failure, it's usually not a good thing.
Yeah, that's why. So the functionality to write is disabled. It can read, it can gather, it can monitor, but you cannot write while we are on the road. You also have no physical access to the ports to use the probe.
So I missed the not being able to write part. Okay. The test port thing is usually, they wouldn't care.
Yeah.
Somebody could plug something in, you get noise, whatever, that doesn't count. But if you somehow disabled the writing during that time, I guess I missed that part.
I did not tell in this presentation that we disabled it. So you don't miss it. Didn't miss it. Any more questions? Then again, thanks a lot.